Good morning. This is Jeffrey Cohen, president and founder of Chicago Quantum. Today I'm going to walk you through a research paper that we published November 4th. Clark Alexander is the other author, and I just want to talk to you about our research. I want to walk you through it so that maybe you don't like to read these kind of technical academic research papers, but you still want to understand what we're about. And so I'm going to try to make this pragmatic, kind of a regular person's explanation. You don't need a PhD in physics or mathematics to understand. But if you have one, call us because we're hiring, and we're doing a lot of great work. And so start off with the title, right? We're picking efficient portfolios, meaning low risk, low volatility, low price risk, high return, where we preserve the beta exposure. So we're preserving your exposure to stock market fluctuations, and if the stock market goes up, you make a lot of money. But we reduce the risk of your portfolio by finding stocks that zig and zag. So an efficient portfolio has the least amount of risk with the most exposure to return. And we do it for 3,171 U.S. common stocks. So it's a pretty odd number. What's that number? That number is every NASDAQ Q stock, every New York Stock Exchange stock, every New York Stock Exchange Tape B stock. These are bigger stocks. These are liquid stocks. This is basically all the stocks, less some data validation. Beta's got to be positive. It's got to have continuous data every day. It's got to have prices greater than zero. Believe it or not, there's a stock that comes out, HCHC, right, normalizes to a negative price. Right? You know, it doesn't make sense, but it's out there, so we have to validate and normalize all that out. And we have a new quantum and classical solver. We actually have a new quantum solver and a new classical physics-based solver that works on the principles of a pressure cooker. So you know, if you if you ever use a crock pot to cook, right? So as you heat up the food, it increases the pressure in the system. As you increase the pressure in the system, it also heats up the food. And so you have this kind of vicious cycle of increasing the pressure, increasing the pressure, increasing the pressure. And then what happens is it bangs against your QUBO, or your problem definition, and it gives you a stock portfolio. It's the craziest thing I ever saw. I got to tell you, it's the weirdest thing that I'm going to use now, pressure. At first we were using just temperature with our simulated annealer, and now we're using pressure. And I got to tell you, these are nice, independent ways to pick stocks. The last pick we made, by the way, we have paying customers. And the last customer that bought a portfolio, the simulated bifurcator, which is what that's called, did an amazing job. It not only picked the two stocks that were picked by Monte Carlo and genetic algorithm, but it picked another stock that was picked by the quantum computer. It picked another stock that was consistently picked with the Dwave simulated annealer, and then it added 3 more stocks of its own. A terrific portfolio, actually, and picked through a pressure cooker. Love it. So we're going to explain to you a bit of what we did. That pressure cooker concept was invented in 2019 out of Japan. We cite the original technical paper. By the way, it had an error in it. The math actually didn't work. I think maybe I don't know if they don't tell anyone, maybe they on purpose made an error, but we got in there, we added another vector, now it works great. It takes a lot of tuning to get it to work right, but that's fine. So, I just explained what we did. So, by the way, the new quantum solver is the D-Wave Advantage. This is a 5,760 maximum hardware available qubits. You don't always get 5,760. Sometimes you get like 5,500 qubits available. And it's in a Pegasus graph size P16 architecture, which is different than Chimera. So what happens with Pegasus, there's a lot more connectivity. So there's more qubits, and each qubit is connected to more qubits better. So my stock can be related to other stocks on less qubits. So how'd we do? What did we do? How'd we do? So we're going to talk to you about the motivation, right, for doing this. Why would you want to analyze every single stock in the United States stock market? Well, duh, so I can pick the best stocks for my clients, the best portfolio. it's one thing to make you give me 64 stocks. You might not have 64 stocks. You might like have 4 stocks that you care about. So Jeff, pick all the New York Stock Exchange stocks and just tell me the best ones, right? Then we do a simulated bifurcator. We talk about it. And then we scale the D-Wave advantage, and we give you our experimental results. A little more of a workman's kind of a paper, right? We don't tell you why the D-Wave advantage should work. We just show you what we did. So we're still using the Chicago Quantum Net Score. We're not going to give you a lot of detail about it, right? But we're still using it. It's a lot of words, not very helpful here. So one thing is 3,171 stocks has a solution space, or what they call a Hilbert search space, of 10 to the 954th power. So I just want to explain that this is computationally intractable. In English, you can't calculate this brute force. Even if every atom in the universe was a computer, they couldn't calculate it, brute force. If you had a computer and you used all the time, since the beginning of time, it couldn't solve it. So we can't. You just can't. It's too big, right? And so you'd need you'd need lifetimes. You'd need galaxies of lifetimes of universes times the number of universes. It's not going to happen. So what happens is when we pick a portfolio, and it's a good portfolio and it makes money, it is better than quintillions of other possible portfolios. This is why 3,000 stocks matters. 40 stocks, 2 to the 40th. Yeah, you're not quite at brute force on my Macintosh, but maybe with a supercomputer. Maybe we go over to the national labs, we could do it. But 3,000 stocks, no. We need like alien life forces bringing us their quantum computers to be able to calculate this. It ain't gonna happen. So it's a big problem. So we're motivated because we want to find the most attractive portfolio of N stocks. So this was a new thing we did. We wanted to be able to pick 64 stocks, or 134 stocks, or 138 stocks. And then from there, right, those are the number of stocks that run on a quantum computer. We want to be able to take those winners, those all-stars, and run those on a quantum computer. So this is a big deal because before we just took all the 40 stocks or 60 stocks and we picked the best portfolio. Now we have an interim step. Step 1, find N out of 3171. Step 2, find the best out of N. It works. And we're using the Chicago Quantum Net Score because we believe that that is the formulation that works the best. By the way, that's a buy and hold strategy for 25 trading days. What are we working on now? By the way, I look over there because that's where my video software is. So we're looking at options pricing. Because it's one thing to buy and hold, right? I'm going to get old holding those stocks for 25 days. I already have some gray hair, right there. But what if I could make money on options? I can make money today, now, on options pricing. And so if you use different measures, you can start to get an estimate of whether options prices are accurate or not. And an inaccurately priced option is just a recipe for profits. If you're an options trader, which, by the way, we're not even allowed to trade options because we are not certified financial analysts. We are not investment advisors or brokers or scientists. So let's dig in. So we talked about it. New York Stock Exchange, all of it. NASDAQ Q, all of it. And the New York Stock Exchange American, which is tape B, which is the stocks. There's like a couple different tapes. One of them has like family trusts or weird stuff, and we don't want that. We want stocks. Right? Our quantum computer can analyze D-Wave's quantum computer, 138 out of a theoretical possibility of 180 stocks. By the way, in this paper, we actually put our citations in. properly. So these are the two papers that talk about the 180 being the theoretical maximum for the D-Wave Pegasus P16 graph size. I know you were like on the edge of your seat. How did you get to 180, right? So we were able to do 138. I'll tell you another motivation. I was at a D-Wave conference, and I said, hey, how many stocks can I put on? And the D-Wave guy said, try 128. Don't go any more than that. It's rough days, right? We're not quite there yet. And so we worked our way up. We got to 134. 134 stocks embeds fully on the D-Wave as a click or a fully connected vertice about 80% of the time. 80% embedding success. That's not bad. It's not bad. If I'm running for a client and I can get 134 stocks to run, and it means 4 to 5 times it works, and when it doesn't, I'll run 10, 15. Let's get it going for the guy, right? And so the other thing that's important to know is we're building a cubo that is 3,171 times 3,171 matrix. We're starting to get a little big on the cubo. It's not to say you can't have a huge matrix with 10,000 by 10,000, but 3,000 by 3,000, you're at a pretty big matrix. I could talk about the workflow. Maybe it's helpful, right? Throw in the keywords for those searches, right? So we first start with the all-in values, and we calibrate the CQ&S value to 0. Now, why do we do that? Because if you pick 0 stocks, the value is 0. If you pick all the stocks, the value is 0, and the solution is somewhere in between, negative. So all I got to do is find the lowest point. I got your portfolio, right? So this is something we've started to do. It just makes it easier to run. It makes it easier to think about it, and logically, it shouldn't, 0 and every stock should be the same if you can do that. The next thing we do, we run our Monte Carlo. We run a discrete probability distribution around n over 2 stocks, and then we run the Monte Carlo for our target size. It's pretty cool. Then we run our genetic algorithm, and I got to tell you, since the paper was published, I now have been really playing around with the genetic algorithms. I want to give credit. There's a guy, master's degree, Davoud Davoud. You see it in social media. I gave him tons of credit. We missed a point on the genetic algorithm. So there's a way to make it a little better, a little more efficient. We've tuned the heck out of this thing, and we have some different ways now to search. Some are more exhaustive, meaning every portfolio is checked against every portfolio, and then you breed it, and then you create mutations. That's an enormous size that you have to then run. The other is more what I call a fast genetic algorithm, right? We have a dance. 10,000 portfolios come to the dance, maybe only 100 hook up and breed. And so I'm just running through generations of like 100 or 1,000 or 10,000, as opposed to a million breeding with 999,999. That's rough. It's rough stuff. So it takes a long time. Then we do our simulated annealer. You know, I love the simulated annealer, right? It was my first custom coded kind of cool thing that I had done. And actually, Clark Alexander, who was a PhD in math, he helped. He provided a lot of coaching and guidance in building a simulated annealer. He's done basically all the hard work of building the simulated bifurcating machine. And rock solid. Rock solid. Knows the markets. So we run that. And then we run the matrix. We build the matrix, right? We build a cubo. And then we run the D-Wave simulated annealer for a target size of n against that cubo. We then run the simulated bifurcator against the target size of n. And then we run the D-Wave taboo multi-start sampler, target size of n. And then we take all the answers, we throw them in a stack, and we run those through a genetic algorithm. So now we're breeding all the best answers independently developed against all the best answers. Boom. We get n stocks. It works. We do a lot of parameter adjustment. Now let's talk about a simulated bifurcator. These are the x values. I just want to give you the intuition. So what happens is you can set all your stocks to oscillate. Up and down, up and down, up and down. It's pretty boring. It's like bouncing a ball in zero gravity. Woo! Bounce, bounce, bounce forever. Right? Doesn't move. No left, no right, unless there's a force acting on it, just up and down. And then we start to introduce the cubo into it. Now it kind of moves. And what we really want is we want to separate out the good stocks and the bad stocks. The good stocks have a positive value. Bad stocks have a negative value. I don't care what the value is, by the way, just positive, negative. And we're going to harvest at different time intervals. What are the good stocks? What are the bad stocks? And you run it and run it and run it and run it. And at the end, what was my last measure? Because it can be a stable system, which separates out. It's hard to see it here in the graph, but what happens is it works. So the good stocks tend to be much more positive. The bad stocks tend to be much more negative, but it's through this oscillation. Boom. You get a matching portfolio. Now we take those, we grab them because they match. I want N stocks. I don't want N plus 1, N minus 1. I want N stocks. 64 stocks, 134 stocks. And I put them in a bucket. And I might run this thing 50 times, 100 times, 1,000 times, 10,000 times. And I basically build my bucket. And at the end, I analyze all the matching portfolios in the bucket, and I find the best one. And I got to tell you, for the client that we just ran it for, which was all the stocks, 3,157 stocks that passed data validation. It was a rough day, by the way, for Yahoo Finance. We found a great 7-stock portfolio that way. Other modifications. So the simulated bifurcating machine in the paper used an icing model. Icing is -1, +1. So I'm either really good, really bad. For us, we have a different model. We're using a cubo model, a binary. 0 means don't buy the stock. 1 means buy the stock. So we have to convert everything all the time from icing to cubo to make it work. There's some math. I could talk about like Kerr constants and epsilons and deltas, Xi, but I'm not going to. Read the paper. And by the way, you won't even understand it from reading the paper. Read our source code, where I'm playing around with all those constants, and then you'll really start to understand it. It's a lot of parameterization and a lot of working with it. And even the number of iterations matters. Epsilon matters a lot, right? It's the speed at which you come to a conclusion, right? We're hill climbing. Do I take big steps or little steps? How many steps do I take? Delta. What's the impact on one axis, X or Y on the other? Kerr constant. What's the impact on one versus the other? Xi. How much do I want to reflect that cubo or have the power of that cubo affect the rest of it? And pressure, I'm just managing the pressure of the system. So it works. Our picks. So in this case, we picked, out of 3,171 candidates, AX, which is a lender. It's a lender in Southern California. And MCRB, which is a biotech platform company. These stocks have nothing to do with each other. We didn't do any fundamental analysis. We just did analysis on the movement of the stock prices. So Axos Financial and Series Therapeutics. And at first, when we ran it, we were very excited because the stocks seemed to separate. And that made us happy because you have your indices in the middle and the stocks separate. And oh, look, one of them popped up 5% right away. That made us feel pretty good, right? In two and a quarter trading days, we already started seeing a profitable trade here. I got to tell you, we checked recently. Wow, this portfolio made a lot of money. If anyone would have read our paper and actually invested in the portfolio, we also put it in medium, by the way, we made a ton of money. Because what happens is the stocks zig and zag, and they oppose each other. So on any given day, the portfolio has less of a chance of a catastrophic loss. but they both have their beta exposure, so they both have their ability to go up when the market goes up. This is what it looked like more recently. Zig and Zag. See the light blue line? That's one of the stocks that went up. The other guy was kind of flat. Then that guy dropped. The other one went up. And they both kind of did their thing, and then they separate out. What's amazing is they were above the market. Made money. Now made even more money. So the point is, we're finding stocks that while the indices are in the middle, the stocks move opposite to each other, but in general, they move well. They move well. They've maintained their beta exposure. Scaling the D-Wave. The new D-Wave computer has 5,760 qubits set in a Pegasus graph size of P16. That's the topology. It has a lot more connectivity over the Chimera topology. I'm going to sound a bit like an advertisement here, but I'm not. We have no business relationship with D-Wave. Other than we're a client of D-Wave, we use their hardware. We love their hardware, by the way. It runs at 15.8 millikelvin, and it's accessed via the D-Wave Ocean Software Development Toolkit through the Leap cloud-based service through an API. So, from an experimental perspective, the D-Wave Advantage 1.1, which is the solver that's available today, runs just like the previous generation. There's a couple of settings that you can't use. Just a different, hang on one second. And it uses the D-Wave problem inspector, which we like. That's the graphical interface after the run's completed. So you can really see how it embedded, how it ran, what the issues were. And so we fully embedded 138 stocks once, but we downsized the problem to 134 stocks in order to get consistent runs. So what changed? It's funny because there's the paper and then there's what we found recently. Let me start with what we found recently. Okay, again, this is a couple days ago. Today, by the way, is November 25th. So we ran about a week ago, right? And the wait time is over. There's no significant increase in wait time at 3 in the morning when you're trying to run this because the markets are closed and you got a paying customer waiting for you who wants to trade in the morning. So at 3 in the morning, no wait time. It's awesome. The second thing was that the Pegasus, when we didn't fully load it, we put 64 stocks, actually 63 stocks on the Pegasus. We didn't get very good answers. It was like there was no stress or tension in the system. And so it's fine. It ran. It was nice. The qubits had room to spread out. It was nice. There was lots of room left over. But I didn't get a good answer. You know where I got the good answer was going back to the Chimera. I went back to the Chimera. I loaded 63 stocks on a 64 stock maximum system. I tuned all the parameters. We increased the pressure. It was like it was awful. It was like a furnace in there. We let the thing run hot too. Instead of 20 microseconds, we were at 100, 150 microseconds. We let that thing bake. So if you know an annealer in a steel mill, you bake that steel and you bake in properties, right? You will line up all the different molecules. Well, we baked those stocks and we got great answers. So I will tell you that just because the Pegasus has more qubits doesn't necessarily mean you get a better answer. We know that because we could compare the D-Wave against all the classical runs. And so a good answer is relative to the classical solvers. So the D-Wave was successful, 11 out of 15 times for 134 stocks. We saw biases. This is the number that you put on the qubit. So you're solving for stock return and you're solving for variance of a portfolio. And so each stock has a certain percentage or portion of that return and of that variance. You put it on. And if you think about it, it can't be 7. What, 700% return? 700% variance? No. So what happens is you build the Cubo, you scale it yourself. We scale ours to about 1, right? 1, -1. And you put it on, and then the D-Wave guys, they rescale the Cubo to place it on the Pegasus. So, crazy biases, right? I don't understand myself. So that's interesting, right? The chain strengths that we found were valid were 0.15 and 1.5. For those technical D-Wave folks, you'll understand that's kind of in the range. Our chain lengths were quite high, 27 to 45 qubits, and our experimental results showed over 100% chain break. So when you fully load the Pegasus, it's not holding back. It's not holding back at all. You've got very long chain lengths. Got a lot of chain breaks. And so what we did is we scaled our QUBO to -4 to 4 instead of -0.99 to 99 because we wanted to make sure that at least the D-Wave simulated annealer, the taboo sampler, the simulated bifurcator had more energy landscape, had more richness of the data to be able to find a valid solution, and it worked better. So scaling your QUBO is something that all of you experimentalists out there should be doing. We vary the number of runs from 200 to 1,000. So similar to what I told you, we bake in the solution with more microseconds from 20 all the way to 150. We can also have it repeat the experiment 5 times more times. So we have more confidence in the solution. As for all methods, we save all of our better or excellent matching CQNS portfolios into a stack, and when we feed that stack to the genetic algorithm. This is interesting because we changed our formulation for the paper, and it's important to know that, right? So what we did is we went from raising the power of the returns for the portfolio to the CQNS power to raising it for, I'm saying that wrong. We went from raising it from each stock's return to the power to raising it to the portfolio to the power. And we did that because we had more confidence in the classical samplers. So we built a formulation that actually was no longer a quantum algorithm. It was a quantum algorithm that was slightly readjusted to run better on classical. And don't tell anyone, but then what happens is you have to send it to the D-Wave, and then it comes back, and then you have to rescore it. So we did that in order to have better classical results. It's about 5% better. And so that was a difference that we did. We keep changing the formulation. We keep trying different things to see how we do. The runtime on the D-Wave varied quite a bit. It varied for the same problem from 85,000 microseconds to 200,000 microseconds. And the number of stocks that we seek in the QUBO mattered. We sampled for 64 stocks, 47 stocks, or 3 stocks, and we did great. But we couldn't find a valid portfolio for 37 or 17 stocks. So it really means that some of our tuning is going to be QUBO stock size specific. So I'm running out of wind here. No one's really asked a question. I'm going to let people know. Go ahead and ask a question. I'm sure people are on the edge of their seat to find out what our experimental results were. I'm now motivated to tell you. So we controlled for the sample size between 3,171 stocks and 134 stocks by setting the CQNS power equal to the log of the variance divided by the log of the expected return. And then we use that same CQNS power for step 2. And this way we could compare the results uniformly across the full set of steps. And we found a good answer. So the best D-Wave quantum solution returned 3 stocks with a CQNS score that was less attractive than our ideal solution. It had a CQNS score of -1.69. So remember, more negative is better. So -1.69 times 10 to the third. It's a good solution. It was better than the all-in 134 stocks, which had a value of minus 6 times 10 to the 5th. So it was like 100 times better, like 50 times better, right? The simulated bifurcator had a score of 4 times 10 to the negative 4. So negative 1.69 times 10 to the negative third. Pretty good solution. It beat those. There's some eye candy. So it was an okay solution. The Dwave did okay. And then I have a whole appendice on how we have to prepare the data and our references. And so I guess at the end of the day, right, so a couple things to note. One of them is the 1-year market return that we're using to estimate future returns is 15.2. And that's because the NASDAQ's up 45.65%. Right? Your Russell's up 10.25. Your S&P 500 is up 18 and a third, roughly. And so we have floors and ceilings, and we use a risk-free rate. The average for the year was 0.65. It's now 0.49, by the way, and we just set it equal to 1. We want to have a reasonable risk-free rate that approximates what a savvy investor can get in a CD. So your markets are up. Your markets are hot right now. And so we're running this evaluation at a time of rising markets. If you look at the Cubit embedding on the Pegasus, you got a lot of room left over. It's nice. If you look at the embedding, you see a little bit of room. Now, it's not a ton of room. It's just a little bit of room. I just want to show you how the same problem embeds differently each time. Simulated bifurcator. What I long to see, I got to tell you, if I could have my simulated bifurcation dream, it would be on the left-hand side. I'd have some stocks that are just up, and we bifurcate. Some stocks go down, and the longer I run it, the more consistent. It's terrific. I'd look over here to the left. I'd have 1, 2, 3, 4, 5 stocks. Pick 5 stocks. In fact, it's 6 stocks. I'm loving life, right? The problem is it's more like what's on the right-hand side. Everything mixes up. You get some stocks that kind of bounce up and bounce down, but you get stocks that cross over. So we'll keep tuning. We'll keep running our bifurcator. We're getting better at it, actually. Now it is a truly useful solver for us. It is another horse in the stable. It's another cylinder in our 8-cylinder General Motors racing engine. So I want to thank you guys for listening. Appreciate it. This article is available on ResearchGate. I think we have like 500-600 reads. Let's see if I can find it for you. Just to show you how to find it. I'm pulling it off stage here, and then I'll drag it over for you. You go to ResearchGate, do a search on the Chicago Quantum Lab or on Jeffrey Cohen, and there it is. Featured research. It's got 660 reads. It's nice. You got our 60 asset paper, or 40 asset paper. The other thing I do, let's see if it allows me to go in through the lab. The Chicago Quantum Lab. We are Chicago Quantum. Got a pretty picture there. Then you can see all of our research. And you see Clark and Alex are there. Not only do you have the paper, but you also have Medium articles, right? We picked 2 stocks this week, trying out the new D-Wave. What happens when we run 72? We see lots of different papers. And so I just want to make sure you get to follow along with our research. And if you're ever interested in joining us, just shoot me an email. If you're ever interested in buying a portfolio, thank you. We definitely can use the business. And the last guy who bought a portfolio spent $750, which, by the way, for us is a lot of money, right? So I was very nervous. And I bought a portfolio, and he goes, Jeff, I paid for the $750 in the first 3 minutes of trading. I was so happy to hear that. I just couldn't take it. So I'll show you where to get it, where you can get to it. You come to our website. It's a nice website. We've actually made it now friendlier for mobile. Chicago Quantum. You click on portfolio. There you go. You can pick up to 3,250 stocks in production. or up to 64 stocks. If you want a quantum run, it's under $50. If you want just classically, it's 50. And there you go. Shop and buy. Analyze up to 3,250 stocks. Come down here, you pick your exchanges. What do you want? How many do you want? Actually, it's how many. If you have a preference, how many stocks would you like us to recommend to you? And then how many of these runs do you want to make? Click buy now. You're off to the races. You pay, and then you shoot us an email. And there you go. So again, thank you very much for listening. And if you buy a portfolio, then I promise you we will do our best always to give you unbiased advice. And we will not trade. We will not act on the recommendations that we make for you. Those are yours. So thank you very much. Have a great day. And for those in America,